Hello, this is Math Kimchi, and today we'll be looking at A Plus Computer Science, which is just a website that where you can practice Java and also just some programming concepts. And today we'll be looking at recursion and more specifically mazes solved using recursion. And yeah, I'll start out by showing some problems I already solved. So this is the most basic problem in mazes, and you basically have to find uh, all of the sizes of the groups of dollar signs, and basically you get the coordinates of each place you want to check. And for example, if they give you 1 comma 1, that'll be this point. You would give 0 because there's no group. It's not even a dollar sign on its own. And another would be 1, 2, 3, 4, 5, 6, 7. And you would return 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. What? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It should return I don't know what's wrong with this, because here it says 16. So maybe it's 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, and the amount of dollar signs in this group would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right. And yeah, you just do the same thing for all the other points. And another thing that will be helpful is the fact that the question will never ask for some 2 points in the same group. So for example, if they already asked you about this point, they will never ask you about another point that's in this group. And what that means is that we can freely manipulate the data, and it wouldn't really matter as long as the only thing you changed was the things in the group you were currently checking. And this is the code to solve that, and it's pretty short, I'd say. We have something called mat, which just stores everything in here, and then we have we just have a main function, and we have something called file, which is a scanner type, and I'm not familiar with this, and my teacher set this up for me, but scanner of file is basically how you read files, and that's how we are going to do it. And it's basically, a file is something that lets you read the file called pr90.dat. And the first thing that's in PR90 is two integers, and we're gonna assign it to RR and CC, and those are these two numbers, so just the dimensions, and we're going to create a new array of arrays, and that's going to be the size that was given previously, and in here we're just gonna like iterate through here we're gonna iterate through everything and find just fill in mat, and then for this we're going to create we're going to take in how many of the coordinates they're going to ask for, and here we're just taking in the coordinates t times, and every time we get a new R and C, we print a new recur, or we print a new like solution. And yeah, this isn't an arrow, by the way, it's t minus minus, which kind of like returns t and then subtracts it by 1, or yeah, I think that's the order that it's in. If it was minus minus t, it would subtract it by 1 and then return it, probably. And so this is pretty normal except for recur, and what recur does is it first of all checks if the coordinates given, so r comma c, is within the range of this array, and if it's out of the range, then it just returns 0, because if the point you're looking at is out of range, then there's not going to be any $sign. And after that, it checks if the current coordinate is $sign or not, and if it is, or if it isn't, then it returns 0, and if it is, it turns itself into a point and it returns a 1 plus, and then the recur of the same point, but 1 up or 1 left or 1 down or 1 right. And this 1 is here because this 1 stands for itself, its own self. And by the way, recur is that's the thing that returns how many $signs are in the specific group. So this 1 stands for the 1 right here, and this stands for how many $signs were in the group that is 1 down, I believe, and this is for how many groups there were for that were connected to the $sign 1 up, and this is to the right and this is to the left. And the reason why we do this is so that it doesn't, for example, go from here and then here, and then it's going to check here, and for this it's going to check like this, but then after it checks everything, it's going to look back at this, and we don't want it to run again, or else we're just going to keep on looking at these two infinitely, or we're going to have an infinite loop somehow. And the way we avoid it is by turning this into a dot once we are done looking at it. And yeah, we just return how many are connected to this r comma c, and yeah, and this works. And yeah, that wasn't really a maze, but it is kind of related. And I'm gonna skip big group because it's basically the same thing. And yeah, let's look at maze solver. So what maze solver does is uh, it just takes in a bunch of mazes and sees if S can go to E if you only go through the dots. And solvable is what we're going to use to see that. And solvable is going to return a boolean, so true or false. And it's also pretty similar. So here we're taking in all the data, and for each maze we see if so the start is always going to be on 0 0, I'm assuming. And so we call solvable of 0 0, and what solvable does is it returns if it is possible to get from r comma c to something called e, and e just stands for end. And in this case it's asking, is it possible to go from 0 0, which is the start, to e? And if it is possible, then it's going to return exit found, or else it's going to print no exit. And so basically what it's going to do first is it's going to check for if it's within the range, and if it's out of range, then obviously it's not possible to get to E. And this, it checks if r comma c is E, and if it is E, then it returns false, or it returns true, because you can always get from this point to this point, and otherwise if it is a hashtag, and in this case a hashtag is wall, so that means that this specific thing is not a legal thing, like you're not allowed to be here right now, so it returns false, similar to this. And the only option left is that r comma c is a dot, and with the dot we can't tell immediately if it's possible or not, so we first turn the dot into a hashtag so that we don't run into an infinite loop. And here we check if any of the four directions, the 4 points connected to r comma c are possible, and if any of them are possible, then we're going to return true. But otherwise, if every single one of them are false, then we return false. And this one works as well. And let's move on to the next one. So count steps is pretty much similar, but instead of returning true or false, we're going to assume that r comma c will always lead to somehow it will always lead to the end. And so also what that means is that there's nothing like where this can either go to this direction or to this direction. we know that every single possible dot connected to this dot right here will eventually lead to this dot, and the start is just the leftmost dot and the end is the rightmost dot. And yeah, so we also have to mark the path by starring the path. And this problem is actually pretty simple in my opinion, all because of the fact that there's only one possible path. Well, I guess you can go back, but we're gonna pretend like we're not gonna do that, because why would we? And this everything like here is pretty much similar, and what we do is check for we find the leftmost dot, and then we call solvable, and this time solvable returns an integer instead of a boolean. And what solvable does is it returns how many steps it's going to take to get from R comma C to the rightmost star, or the rightmost dot. And excuse me, yeah, once we call R comma C, we have if it is out of range, then you have to return the smallest possible integer. And wait, I feel like I should have done the max value for this. That's weird, but I guess if it works, it works. But yeah, it does make sense to make it max value, unless there's something that specifically looks for, like, checks if there's like a negative value. And yeah, I'm just gonna check that what I just didn't break anything. Yeah, so it's still working. And basically what we do is we say that if this is out of range, then it's gonna take the max value, and it's technically some number, like, I'm not sure. It's a pretty big number. It's like 2 million or something. But that's not the point. It might as well just be infinity. And if we are currently in a wall or a place we have already been, then we also return infinity. And this doesn't actually mean that if R was, for example, -1 and C was 2, then it's going to take infinity steps to get to the ending point. All it really means is that we're going to ignore this what we just returned and whatever called this function, because we're looking for the shortest possible path. And yeah, it's gonna ignore the max value the moment there's something that's less than the max value. And same with this, because it's impossible. And for this, we could actually do like, yeah, something other than max value. But the problem with that is that or the reason why we're allowed to just say it's gonna take an infinite amount of steps is that we know that whatever however long it's gonna take to go from this current r comma c to the end is not the shortest path, because it means we have, like, walked back and we're gonna walk forward again. So we just return basically infinity, saying we can ignore this. And now we check if r is at the most right, and if it is, we finally change it to the star, and we return a 0, because it takes 0 steps to get from the end to the end. And otherwise, we turn RC to start again, but this time it's so that we don't walk back into it, and we return the smallest number that up, down, right, left leads to, and we just add 1 to it. And as you saw previously, this also works. And yeah, well, actually, this keep in mind that this only works if we know the maze is solvable, and there's only one possible solution, ignoring, walking back. And yeah. There's also something called the shortest path. And oh yeah, I don't think this matters because it's pretty much the same thing. There's also portals, which was a little more interesting, but this one, all you had to really do is check if there was like a number, and if there was a number, then you had to change the current thing to lowercase p. Well, you could have changed it to like a wall or something, but I just thought it might be useful to remember it. And you changed it so you wouldn't walk back into it, and you looked at every single possible position for the other number, the other digit of the same kind. And once you did find that, you returned solvable for that new location. And grass mapper wasn't too interesting. And yeah, I guess we can work on 3D maze now. And I actually have already worked on it, but the problem right now is that it doesn't find the shortest path. And let me explain to you how it works, so you guys can get an idea. So this is actually pretty much the same thing as any 2D maze we have previously programmed, but we just need a third dimension to it. And we have a new variable called HH, which is like the total height. And we create a new matrix. I think that's what MAT stood for. And we, just create a new character array with the correct dimensions. And yeah, this is basically the same thing with, I think, one extra for loop. And this is just filling in the data for Matt. And then we have something called steps. Wait, let me just run this. Right. Yeah, so I was in the process of uh, changing this completely. And oh wait, I don't know why I had steps in here, but all of these things are here because I copied it from I copied this entire code from one of these 2D mazes and just added a third dimension to it. And yeah, the one that I copied from, I guess, asked to print out the new path, but we won't be needing that. And yeah, I'm pretty sure these 3 comments I had it so I could check what was wrong. And yeah, there's also, yeah, basically this looks at every possible point in the maze, and it looks for the starting point, and then it finds how long it takes to get from the start to the end, and it just prints it. And then the program ends, I guess. Although, that's weird. I don't think this break actually does something, because this break only breaks out of this. So it does do something, but it doesn't have the full effect I wanted it to have. But it doesn't matter. And also we can't return after this because I still want this giant loop to continue. But anyways, this is solvable, and it looks at, the current RCH, and it checks if it is out of bounds, in which case, it should return the max value. And it also checks if this is a wall or if we've already been here, in which case it also returns infinity. And if this is the end, then we can just return 0. After turning this into marking this as a place we've been to before. Although I don't think it's necessary because we don't have to print out the final thing. But I guess it doesn't do any harm. And otherwise, we also, it means that we're at a dot, and that's a path that we haven't been to before, so we mark it as somewhere we've been to before. And then we have S, which stands for, I don't know, shortest probably. And it starts out as, yeah, and we do, we find if this is smaller than the previous max value, and we do that for every all 8 of the directions: up, down, right, left, and front, back. And we compare it, and we make S the biggest value out of all of these. and then we return s plus 1. And if we run this, it doesn't work. And that's interesting. Oh, right. Maybe if we, I think the problem there was that it went all the way from the max value back down to negative. And wow, I guess I just fixed the program. And yeah, the problem before was that we actually couldn't do completely max value, because then if we did max value plus 1, then it would like reset all the way from max value back down to the smallest possible value, which was like negative 217 blah blah blah. But yeah, I guess I just fixed this program, and this also works only because there's one possible path, obviously ignoring walking back. And yeah, just to recap, what solvable does is it takes in coordinates, and it checks if it's a legal coordinate, and if it's not, it returns infinity, and if it's a wall or someplace we've been to before, it also returns with infinity. And if this is the end, it marks the end as someplace we've been to before, and it returns 0, because it takes 0 steps to get from the end to the end. And then it sets and otherwise that means RCH is a dot, and in that case we're gonna mark it as someplace we've been to before, and then we just look at every possible 6, oh yeah, I guess it's 6 directions, not 8. We look at all 6 directions that, or all 6 points that touch RCH, and if any of those, and I guess we find the smallest out of all of those, and we return the smallest it takes from something adjacent to us, and we add 1 to it, because it takes 1 to get from our current place to whatever place is adjacent to us, and it takes S to get from the place that's adjacent to us to the end. And yeah, that's pretty much it. And I hope that was kind of interesting or fun, and thanks for watching.